little chart here, this is a list of number of distributions. Well, I mean, in this study here, so it's saying there's about 20. I tried to count them up. I didn't get 20. I don't know. That's why I'm not so good at math. I suck at counting things. But anyway, each one of these things up here, I can't read them even. You probably can't read them either. But each one of these squares is a distribution method. And you can see a lot of them are kind of interrelated, you know, in different ways. You can put together these distributions, different ways of analyzing distributions, putting them together with other ways of analyzing distributions. Yeah, this, I would love to get into this. You know, I might someday if I live long enough, which I probably won't. But anyway, what can you say? So I decided so these I have the link to this little one here, be up there. Now, I thought I'd just read one of these. So this is the Cauchy, if you say that right, Cauchy distribution, which is on here somewhere. There's the chi-squared. Oh, here's the Cauchy, right here. This is this one over here. Where's it's not that one. This one. This one right here says Cauchy. That's the Cauchy distribution. Get my fingers right. Okay, anyway, it's that one. And here's what it says. I'm just going to read this. What do you think? This one? This one? I like this. Okay. Cauchy distribution is employed in mechanical and electrical theory, physical anthropology, and measurement and calibration problems. In physics, it describes distribution of the energy of an unstable state in quantum mechanics under the name Lorentzian distribution. I don't know if that's the Lorentz curve. I don't know. You'll see a lot of these use, as that chart shows, there's other distributions with other distribution methods. The Lorentz curve, anyway, probably not even that. Another application is to model the points of impact of a fixed straight line of particles emitted from a point source or in robustness studies. Robustness studies, I just know from reading a few of these, robustness refers to resilience and stability. So when you got these charts here, like the percolation, you start to wonder, how stable is it? There you are. How stable is that? How resilient is it to different kinds of percolations, right? Different pathways. Is it flexible or not? Well, you can look at that. You can probably add a number of these things together. The Cauchy distribution is known to be a pathological distribution, as both its mean and variance are undefined. Sorry about that. What can you do? Oh, it takes two parameters. I don't know why that's so pathological. I'm sure it is, though. Okay. In Bayesian statistics, Cauchy distribution can be used to model the priors for the regression coefficients in logistic regression. The Bayesian, like you'll see Bayesian distribution in a lot of places. I don't see it on that chart, but Bayesian statistics is within these other methods. So, man, got to know your statistical methods here. The distribution takes two parameters, the mode M corresponding to the peak and the scale gamma, half width at half maximum of the distribution. Sounds very Gaussian. Okay. Cauchy distribution is the student's T distribution with 1 degree of freedom. That's another one. I saw that one on here. Student's distribution. That's another statistical analytical method of distributions. But no, I don't see the student on there. But they talk about it in other places. Like Bayesian's not on there, but they talk about it. student's not on there, but they talk about it. It was in the description if you want to read the thing. But anyway, here's what the Cauchy distribution might look like. So there's the actual, like here's a formula. You know, these things like this would be sort of the simplistic setup of the problem, and this would be a formal working out of the problem. Just like we had that simplistic model where P is going to be greater than threshold, equal to the threshold, or less than the threshold. Sometimes that'll be presented as P is equals 1, and if that's a percolation, so P minus 1 is the condition where the percolation does not have a node there, right? Percolation not going to move through there. That's the P minus 1. They'll represent it that way too. But then, you know, it gets super complicated after all that. So if we go back to this, what we have here. So what you can do with this, one of the things I've seen is like this can be a population. These can be different groups of people or groups of other organisms, and how they're distributed, and then how something might move through the group, like an idea, is it going to move through the group or not? Some groups, no, not going to get anything. But, you know, say like a predator or maybe a pathogen, right? So you can see how is the pathogen going to move when things are distributed like this, when they're distributed like that. Why might the distributions change as, say, a pathogen moves through there? You can get into all kinds of these things. Now, gee, I think that's everything. Yeah, right. I think that's everything that I have here. Well, I hope you like the picture. The girl's very nice. And let's see here. No, I think that's it. So we can go back to this. So now, you know, I think you can maybe better understand that we're talking about word and concept usage. So the word and concept usage is the element that's moving through these distributions, like words and ideas and thought, right? How well is an idea going to move through a network like this? It's a neurological network, right? Or how well is an idea going to move through a network like this? And how is a network like this going to be able to express? When and why will these things change? Why do these networks change as things are happening? As something goes through there, hopefully they're changing. This one's going to be much more flexible and adaptable. This one much less. So anyway,